Welcome to our introduction to neural networks. Today we'll explore how these algorithms work, from their biological inspiration to practical application. We'll focus on understanding the core concepts that make neural networks so powerful. On the next videos, we'll dive into their implementation using PyTorch. So our learning goals are to understand what neural networks are, explore how they learn, break down their key components, and discover how their weights are trained using gradients and loss functions, as well as the purpose of train, validation, and testing data. By the end, you have a solid understanding of the core neural network concepts. The story of artificial neural networks begins in 1943, when a collaboration took place between Warren McCulloch, who studied how the brain works, and Walter Pitts, who specialized in logic. They created a mathematical model of neurons functioning as logic gates. Looking at the image, you can see the parallel between a biological neuron at the top and the mathematical model below it. Just as a real neuron receives inputs through its dendrites and sends outputs through its axon, the artificial neuron takes X inputs and combines them to produce outputs. This mathematical abstraction, that we also call a processing unit, captures some essential features of a biological neuron. Biological neurons take multiple signals, process them, and produce an output. While very simplified, this model proved to be powerful. It is the basic building block of all artificial neural networks using modern machine learning and current artificial intelligence. McCulloch and Pitts showed that by connecting these simple units together, we could create networks capable of performing complex operations, much like our brains process information through networks of connected neurons. Perceptrons were a follow-up on the work of McCulloch and Pitts. They were invented by Frank Rosenblatt in 1957, and they were the first neural networks trained with data. They were designed for pattern recognition tasks, particularly visual perception, which is where the name perceptron comes from. Rosenblatt used them to perform basic geometric classification and character recognition. His most famous demonstration was the Mark I perceptron machine that he built at Cornell University. This could recognize simple patterns using an array of 400 photocells connected to perceptron weights. These weights were adjusted using potentiometers and a simple update rule that Rosenblatt defined. The fundamental idea of a perceptron is to compute the weighted sum of input features, including a bias unit, and then to pass this sum through a step function or other nonlinear activation to produce an output. Then we evaluate how good the result is and use this information to update the weights, so that the next predictions with similar data points are better. These ideas are still used today and form the basis of modern neural networks. In the 70s and 80s, the backpropagation algorithm was introduced, and people started training multilayer perceptrons as fully differentiable functions. A multilayer perceptron stacks the components that we saw before. We call input layer the layer that takes the X input features, which in the case of images are pixels. We call the output layer the one that produces the final prediction output, and the hidden layers are those that are between input and output layers. In this illustration, we have a single hidden layer, but modern neural networks can have tens, hundreds, or even thousands of hidden layers. Stacking layers allows us to do complex mappings between inputs and outputs. So modern multilayer perceptrons are powerful and can be used for both classification and regression tasks. To explore their use in regression, let's examine a concrete example, predicting the price of a 1964 Chevrolet Corvette Stingray, which is a collectible vintage car. These cars are very valued by collectors, so this might be an interesting use case for studying how neural networks learn from image data. To evaluate the model's performance, we need a measure of error to determine whether the network is using appropriate weights. In this example, we will use absolute error, which measures the difference between the true price of the car and the neural network's output. To keep this demonstration simple and visual for teaching purposes, we will use an extremely minimal dataset consisting of just 3 images, one for training, one for validation, and one for testing. While this is not a realistic approach for actual applications, it serves as a clear example to understand the basic concepts. In practice, datasets are normally much larger. At a later part of the course, we will repeat this task with the Stanford Cars dataset. In neural networks, weights are the adjustable parameters that determine how strongly one neuron influences another. You can think of weights as roads connecting cities. Here we have a fully connected network with one hidden layer. If the input is an image, the number of input neurons corresponds to the total number of pixels multiplied by the color channels. For example, with 3 color channels, red, green, and blue, each pixel in those channels becomes an input node. Every input node connects to every neuron in the hidden layer, and each connection has a distinct weight, a floating point value, usually near the range from -1 to +1. To predict the car's price, we don't alter the input pixels. Instead, we adjust these weights to reduce the error. We measure the error using a loss function. In this case, is the absolute error, the absolute difference between our prediction and the output of the network. A forward pass through the network generates a prediction, and we later compute this loss. Then, via backpropagation, we calculate the gradient of the loss with respect to each weight and update the weights in the direction that reduces the loss. We propagate the error backwards from the output unit to all of the weights in the network, computing how much each of them contributed to the total loss value. This backpropagation process is automated in most popular deep learning frameworks. In our practical exercises, we will use PyTorch's implementation of automatic differentiation, which we call with backward, to do these adjustments to the weights. So, we have discussed that training a neural network means iteratively adjusting its weights to minimize error. For this, we use gradient descent, which adjusts weights step by step in the direction that reduces the loss, the gradient, or better said, the negative gradient. The learning rate controls the size of these steps. A learning that is too large might miss the minimum value of error, while too small of a learning rate slows down learning. A weight is often written as W subscript ij, where I is the input neuron and j is the output neuron. We typically start with random weights and then update them based on the partial derivative of the loss with respect to each weight. And if a weight increases error, we decrease its value. If a weight decreases error, we increase the value of that weight. In the diagram, the red line highlights one weight being updated. The orange line shows how this weight influences the final output. Because we systematically use calculus to do these adjustments, we make informed changes instead of random tweaks. We keep repeating this process until the network's overall loss converges to a minimal value. At the final layer of a neural network, we have a loss function. The loss function that we use in a neural network is a differentiable function that guides the adjustment of the weights of the network. The loss function is tied to the task. For regression tasks, we would use something like the mean absolute error or the mean square error. For classification tasks, we would use the categorical or the binary cross entropy. We will delve into these functions in a lot of detail in later videos. A very important part of the network's structure is the matrix multiplication that happens between features and weights. Every column on the feature matrix should match a row on the weights matrix. In this diagram, the number of weights matches the number of input units, producing a single output unit, like what we will need to produce when predicting a single number, such as the price of the car. We can have a layer with this structure on the output of our network. And then, in general, we need to think that the number of columns in the weight matrix, if we place it first, should agree with the number of rows on the features matrix, which is the number of input features. For an image, this would be every single intensity value on every channel that we have on the image. If these dimensions match, we can map any number of input units to any number of output units. The dimensions of a layer are defined by the dimensions of the weight matrix that produces it. For example, if we want to have 4 processing units in the hidden layer of a neural network that has 3 units in the input, then the dimensions of the weight matrix for that hidden layer should be 4 rows and 3 columns. So we have discussed that training a neural network involves refining the weights to minimize the error in our predictions. By applying backpropagation, we calculate how each weight affects the loss function, giving us gradients that point in the direction of steepest descent when we use the negative sign in front of the gradient. We then adjust all of the weights of the model in the direction that reduces the loss. In the 3D loss landscape that we see, there are about 7 consecutive weight updates. Each update is computed by multiplying the gradient by the learning rate, which determines the size of each step. A well-chosen learning rate helps the model steadily decrease its loss without overshooting the region of minimal error, which is shown in blue. We use the training image to calculate these gradients, or the training dataset to calculate these gradients, and update the weights. However, it's also important to monitor the performance of the loss on the validation set, the validation image. And we want to keep the weights where the validation loss is minimized. This tracking is super important when we train a neural network. In this plot, we see how we track both the training and validation losses. As the network learns a compressed representation of the training data, it's natural for the training loss to decrease over time. What we really want to do is to checkpoint this and save the model that achieves the lowest validation loss. We care more about performance in the validation set than in the training set, because the validation loss serves as a proxy for how well the model will generalize on the test data. Note that each pass through all of our training data is called an epoch. This terminology is important for us to remember. We can say that the model is at its best fit in epoch 34. It's underfitted before epoch 34 and overfitted after epoch 34. The final benchmark for our algorithm's performance comes from the test set, which provides a true measure of how well the model generalizes. Remember that the validation set is used to configure the model, for example, to decide when to stop training, when to checkpoint, and therefore we cannot use the validation set as our final indicator of performance. This distinction between validation and test sets is very important for every machine learning practitioner to remember. So to wrap up, we have explored the foundations of neural networks, going from components to model benchmarking. We discussed multilayer perceptrons, emphasizing how weight updates are guided by the loss function and gradient descent. In the next sessions, we'll dive deeper into implementation using PyTorch.